Welcome to Spring LIB.
So part A asks us to graph the force as a function of r, and this would be the graph here. You can use Excel or MATLAB or any graphing software in order to model this. And then for part B, let's figure out the equilibrium position. So for part B, we can say that the force of r naught equals negative c over r naught squared plus d over r naught cubed. At this point, we know that this is going to equal 0 because we want to find the equilibrium position. Therefore, c over r squared equals d over r cubed. And so essentially, the equilibrium position, r naught, this will equal d over c. So this would be our answer for part B. Now, for part C, we're trying to find the net force at r equaling r naught, the equilibrium position, plus the change in r delta r. So we can say that f of r plus the delta r would be equal to negative c times r naught plus delta r. We're simply just substituting. And so at this point, we can say that f of r plus change in r would be equal to negative c over r naught squared times 1 minus 2 delta r divided by r naught. So we have to make an approximation, plus d over r cubed. And then this would be 1 minus 3 delta r over r naught. And so at this point, we can further simplify and say that this is going to be equal to c over r naught cubed plus negative r naught times 1 minus 2 delta r over r naught plus d over c, and then this will be, again, 1 minus 3 delta r over r naught. We can say that f of r plus delta r equals c over r naught cubed, and then this will be minus r naught plus 2 times delta r plus r naught minus 3 times delta r. And we can cancel out these and say that f of r plus delta r will equal negative c delta r over r cubed. And it's important to note that here the force is going to be directly proportional to the change in position. However, it's going to be in the opposite direction. So force is directly proportional to the change in position and in the opposite direction. This would, again, model simple harmonic motion or simple harmonic oscillator. So at this point, for simple harmonic motion for part D, for simple harmonic motion, we know that force equals negative kx. Therefore, k is simply equal to c over r naught cubed, and this will equal c to the fourth over d cubed, given that r naught equals d over c. So we plug this into here, and we cube it, and this would be equal to the spring constant. So this would be your answer here. And then for part E, lastly, we want to find the period. So for E, the period is going to equal 2 pi times the square root of the mass divided by the spring constant. So this would be equal to 2 pi times the mass times d cubed divided by c to the fourth. And so this would equal the t, the period. So this would be our final answer for part E. That is the end of the solution. Thank you for watching.